Hi everybody, this is the last presentation on the topic of integer programming, and this presentation covers section 9.4, 9.5, and 9.8 on your textbook. And by the way, if you experience any difficulties during this studying from home period, please feel free to email me. I might be able to help or I may not, but then just feel free to talk to me, okay? If you watched the previous video, I've talked about how we are using the branch and bound method for solving pure integer programming problems. By pure integer programming problems means that all variables needs to be integer. Now let's see how we can use this to solve mixed integer programming problems. In the mixed integer programming problems, some variables are required to be integers while others are free. For example, in this problem, you see that we have x1 and x2 variables, but only x1 needs to be integer. x2 can take any real value as long as it's greater than or equal to 0. As usual, I mean as what we did in solving the pure integer programming problem, we begin by solving this problem using the LP relaxation. Means that we relax any constraint saying that any variable needs to be integer. So we pretend that all variables can take any real value. That's the LP relaxation. And then we obtain from the LP relaxation, this is the optimal solution. We see here that x1 is not integer, therefore it's not a feasible solution yet for the original mixed IP problem. Then we must branch on x1. See that we don't care about x2 because x2 does not need to be integer. So here we only care about x1. x1 is still not an integer, so we decide to branch on x1. As usual, you need to create a tree to record your journey through the branch and bound process. And then every time you solve a subproblem, you update this tree. So we have had subproblem 1 so far, which is the LP relaxation. And we see that x1 is still not an integer, so we are branching on this variable. So x1 equals 2 over 3. 2 over 3 is between 0 and 1, so we edit constraint saying that x1 needs to be less than or equals to 0 or x1 greater than or equal to 1. Okay, because this 2/3 is between 0 and 1, and while you're branching a variable, you need to say 1 is less than or equals to an integer that is less than that, and then greater than or equal to another integer that is greater than the original number. So less than or equal to 0, greater than or equals to 1. We arbitrarily choose to solve subproblem 2. So solving this one. And then subproblem 2, when you solve it, you get the optimal solution is that x1 equals 0, x2 equals 3. Now, this is a feasible solution for the original problem. That's why we say this is a candidate solution. So we update the tree with subproblem 2, which is now a candidate solution. And then we fathom this subproblem because we don't need to branch it any further. We move to solve subproblem 3. And then when you solve subproblem 3, you see that it gives a higher z value. 7 over 2 is higher than the candidate solution from subproblem 2. So now subproblem 3 becomes the new candidate solution, and actually it is the optimal solution for the problem because x1 is already integer and then x2 we don't care about that. So actually we have got the optimal solution for the mixed IP. So that's how we are solving a mixed integer programming problem. The only difference with the previous one is that now you only care to branch a variable that is restricted or constrained to be integer. The other variable which is not constrained, you can just ignore it as it is. The other procedure are exactly the same. And here, since there are only two variables involved, you may solve it using a graphical approach, which is not shown here, but is exactly the same with the previous video. You may want to really redo this problem using the graphical solution and graphical approach, to find the solution for subproblem 1, 2, and 3. Make sure that you're really able to get this solution instead of just looking at this tree and saying that, okay, I know how it works. It's one thing to know how it works, but it's another thing to really experiencing how to do this. So I strongly suggest you to really try solving this small problem, okay? Next, we are going to see how we can solve knapsack problems by branch and bound method. We have seen this knapsack problem several times. I think we've seen this in the dynamic programming chapter, and then we've seen this again in this chapter, integer programming, in the section 9.2. So knapsack problem is an integer programming with a single constraint. So in the objective function, we want to maximize the total benefit that we obtain from all items that are possible to be taken with us in our knapsack. So knapsack is a big bag, and then you have a lot of items like 1, 2, 3, up to n items that you can take into the bag. And then each item will give you a particular benefit. So item 1 gives you benefit C1, item 2 gives you benefit C2, and so on. But then your bag has a particular capacity that you cannot exceed. So B is the amount of available resource or the available capacity of your knapsack or your bag. And then A here is the amount of resource, or if you think about the bag, how much space each of these items use inside the bag. So A1 is the amount of space or resource that is used by item 1. A2 is the amount of resource used or taken by item 2, and so on. So you want to maximize the benefit by taking the items, but then each item will take space in your bag. And then your bag has a limited capacity. So obviously, most of the times you cannot take all the items that you want. So here the problem is we want to optimize the maximum benefit that we can get by taking the items such that the capacity of the knapsack is not exceeded. Now let's look at the variables. Each variable is a 0 or 1 variable because each variable corresponds to the decision whether you take that item or not taking that item. Let's say if x3 equals 0 means you are not taking item 3. But if x3 equals 1 means that you are taking item 3. And so it is the same thing for all the other i's. So for all items, you are going to decide whether you're going to take it or not. If we solve this problem using branch and bound method, when we branch a variable, then the result will be we are having two subproblems with the constraint saying that for the first one, xi equals 0, and for the second subproblem saying that xi equals 1. Why the sign are equalities instead of less than or equal to or greater than equal to? Well, because the variable must be exactly 0 or exactly 1. So when you branch on a variable, the results are xi equals 0 or xi equals 1 exactly. Now, when we solve the LP relaxation, and also actually when we solve the other subproblems in this knapsack problem, we can solve it easily by not using graphical approach, not using simplex approach, but using this simple approach here. So first we sort the items from the highest CI divided by AI. Remember, C is the benefit of taking item I, and then AI is the space, capacity, or resource that is consumed by item I. So we sort the items by the highest ratio of benefit over resource that it consumes. Now, after you sort all the items, you just put the item into your knapsack based on the order until your knapsack is full. And then we perform this step each time, followed by a branch and bound method if there's a non-integer variable. So if everything is already integer, means that you take item 1, one item, item 3, one item, and so on, then it's done. It's the optimal solution. But if there is a variable, let's say you are taking item 5 as much as 1/3 of item 5, then you need to perform branch and bound. You branch on that variable, you get the subproblem, and then you resolve that subproblem using this method. Check if there's still any non-integer variable, you perform branch and bound again, you get new subproblem, and then you return to this. So you keep doing these steps until all variables in your subproblem solution are integers. Here's an example of what I was just talking about. So we have this knapsack problem. We want to maximize the total benefit, but then we have the constraint that each item will consume some space in your knapsack, and your knapsack has only a capacity of 100. So remember, first step is we are solving this by computing the ratio of CI divided by AI. So for item 1, the benefit is 40, and the resource it consumes is also 40, so the ratio is 1. Let's say item 5 here. Item 5, the benefit is 4, but it consumes 10 of the space or capacity in your knapsack. So the ratio is 4/10. So now you have all this ratio, and then you sort these items from the highest ratio. The highest ratio is item 7 here with the ratio 2. So that is the first item that we put in our knapsack. Now you put item 7 in your knapsack, you check how much remaining space you have in your knapsack. So item 7 consumes 30 of the capacity. So now from the original space 100, it goes down to 70. Next, you try to find the second item with the second highest ratio of CI over AI. Apparently it's x2, 8/5. So you again decide to take that item. You take that item and then you check you still have remaining space of 20, because item 2 consumes the capacity of 50. So from 70, your knapsack's capacity goes down to 20. Check again the third highest ratio of CI over AI. There is a tie actually between item 4 and item 1. Both have the ratio 1. So you can arbitrarily or randomly choose item 4. And then if you take item 4, it consumes the space of 10. So you still have remaining capacity of 10 in your knapsack. Next, you can take item 1. but you can only take 1/4 of item 1. Why is this the case? Well, notice here that your knapsack has remaining capacity of 10 at this moment. So you've taken item 7, 2, and 4 such that the remaining capacity is only 10. Item 1, however, needs the space of 40 in the knapsack. So you only have remaining space of 10, but the item you want to take needs 40. So yes, you may take that item, but only 1/4 of it. Because the remaining space is 10, but the required space is 40. So you just take 1/4 of this item. Of course, it's not possible to take just 1/4 of the item, because in the beginning we have said that the decision is only take an item or not taking it. You cannot take any fraction of an item. Now, because all variables need to be integer, of course we cannot allow x1 to be non-integer, 1/4. What you're going to do now is branching on that variable. Means that now you have a subproblem 2 with the constraint x1 equals 0 and subproblem 3 with the constraint x1 equals 1. Remember, we are now in the 0, 1 integer programming. So when you're branching a variable, it becomes the variable equals 0 and the variable equals 1. Do not be confused between this 0, 1 integer programming with the previous videos when we talk about mixed integer programming and pure integer programming. Okay, now let's see if you have x1 equals 0 in subproblem 2, what you're going to do is that first you set x1 must be 0. And then the remaining space in your knapsack is, of course, it's still 100 because you're not taking any item. But then when you're looking at the table Ci over Ai, you ignore item 1. Why? Because you already decide from the very beginning that x1 must be 0. So just ignore item 1 and do the process as usual, which means that you start from the highest Ci over Ai, try to put it in your knapsack and compute the remaining space and so on. The same thing here in subproblem 3. I really want to emphasize that when you start with a constraint saying that x1 equals 1, before doing anything, you must set this decision. Say that you take one item of x1, you take one item of 1, I mean. So the remaining space is now 60 because item 1 consumes the space of 40. So now after you're setting this, then you may start doing the picking the item based on the Ci over Ai order. Remember, you really need to start by setting this before doing anything else. Now, the textbook does not show the full computation of finding the solution of this problem, but you may want to try to really compute this by hand, such that in the exam when you're seeing this kind of problem, or you meet some kind of difficulties, you really know how to handle those. The textbook actually provides the complete solution for another problem. So here's a Stockco problem. You are given the formulation and you are given the entire tree for this problem. And then also I think it gives you the optimal solution. So try to do this exercise until it is complete. So you start with subproblem 1, then you can follow this the order that this tree is constructed. So that is t equals 1, t equals 2. This is third step, fourth step, fifth, sixth, and so on. Try to do all these subproblems. And what I would like to emphasize here is that, see, let's say we are doing subproblem 5. Notice that there's already constraint here saying that first, here it says x3 equals 1. Here it says x2 equals 1. So before you are putting any item in your knapsack, you must make sure that in subproblem 5, x3 equals 1 and x2 also equals 1. So before doing anything, you must put item 3 and item 2 into your knapsack when you are doing subproblem 5. Why? Well, because you are following these branches here, so you must satisfy all the constraints in those branches. Okay, so let's say you're doing subproblem 6. It means that since the very beginning you need to fix x3 equals 1, x2 equals 1, and then x1 equals 0. So you fix those variables at those values before you're adding any other item to your knapsack. Okay, I really strongly suggest you to do this exercise by hand from subproblem 1 until you get the optimal solution. I think I'm going to cut this video at this moment, so also for giving you time to solve that previous exercise. And on the second part of this topic, I will talk about another algorithm, which is called the cutting plane algorithm. So this algorithm can also be used to solve an integer programming. In the meantime, please do the exercise in the previous page. Thank you.